All right, hello everyone. Let me first thank Denise and Osvaldo for the invitation. It's very nice to be here. This talk is based on joint work with my co-authors Uri Adar, which is my student, and Jingbo Liu and Yuri Polyansky from MIT. And it's going to be presented in this talk next month in Phoenix if you happen to be there. So what is the setup we're considering? So this is a high-level description of the setup. I'm going to make it a little bit more precise in a minute. There is some joint distribution, PXY, which is unknown. And Alice and Bob, two remotely located agents, are observing ID samples from this distribution. Alice is observing the X component, and Bob observes the Y component. And they'd like to get an estimate specifically of the correlation between X and Y. Okay, we could talk about other measures, but here we're going to focus on a correlation. And we're going to think about a regime where basically the distributed nature of the problem is the central issue, because we're going to assume there's a number of measurements that they have, n is basically infinite. Okay, it could be any number. So if they had been co-located, there wouldn't have been any problem. They could have estimated PXY arbitrarily well. So it's not interesting when they're co-located, but once you separate them, they need to communicate, and we're assuming that they can, specifically we're assuming that they can interactively exchange k bits, so they could go back and forth in an unlimited number of rounds. And the question is basically, how well can they estimate the correlation given that k is fixed and n is arbitrarily large? So there's, their goal is to estimate rho. Specifically, let's imagine that Bob is estimating it, to give an estimate rho hat, which has low quadratic risk. And we're going to actually talk about specific distributions, specific families of distributions for a good reason. One of those is the case where X and Y jointly normal with unit variances and correlation rho. And the other one, which is kind of similar, is the case where X and Y are binary plus minus 1 with zero mean and, again, correlation rho. What's nice about these distributions, first of all, is that the marginals do not tell you anything about the correlation. If you learn anything about the correlation of the marginals, then again, this problem becomes trivial. And also, you can show that this is basically the worst case. So if PXY is not even known at all, you still want to think about this problem. All right, let's make it a little bit more precise. So again, we said PX and YN is a product of PXY. And let's call the message sent by whoever, either Alice or Bob, on round I, let's call it WI. And what characterizes the protocol communication is this collection of Markov conditions, Markov chains. So let's look at Alice. Imagine Alice is speaking first, so Alice speaks on odd rounds. Basically, Alice is saying WI as a function, computes WI as a function of xn, which is her input, and WI minus 1, which is everything that had been said so far on the channel between them. And given that, whatever she says is independent of what Bob has. Okay, this is the definition of interactive conversation, and the same for Bob with switching the roles of x and y. And you could just put all those messages together, W1, W2, and so on. There could be an infinite number of those into what we call a protocol or a transcript, whatever you want. We kind of mix the two notions. And this protocol pi, which is the entire conversation, we want it to satisfy a condition, which is that the entropy of this entity should be smaller or equal to k, which is the number of bits we're exchanging. And at the end of communication, or at infinity if you want, Bob produces an estimate rho hat, which is a function of the protocol, the transcript, what he has seen during conversation, and of his own local samples. We're going to care about the minimax quadratic risk, specifically the global minimax quadratic risk, which is this function. So we're fixing some rho. It's unknown, but let's think about some rho. We're looking at the expected quadratic error of the estimator, and we're supermising over rho. So we're taking the worst case correlation for this MSE. And then we're infamizing over all protocols, all estimators, and all dimensions. Okay, so this is the best you can do in the worst case. And we're going to call this R star. So it's a function of k. K is held fixed. Okay, k is the number of bits. So we're going to care about this. We're going to try to characterize this quantity. You're also going to characterize what we call the local minimax quadratic risk, which is a similar beast. The only difference is that here somebody's telling you in advance that rho lies in a certain delta interval around some specific rho. Okay, so the correlation is almost known. Okay, it's known to be very close to some specific rho, and you still want to know what the min-max risk for this specific interval is. Okay, so it's a local version of this. But we're mostly going to focus on R star. Yeah.
So quick question. H is computed with respect to the joint, the true unknown.
Yeah. So yeah, it's true. That's a good remark. So everything, all the mutual informations and entropies that I'm going to talk about is going to be computed according to the correct correlation, whatever correlation it is. Okay. Yeah. All right. So here's the main result, basically, in a nutshell. We characterize quite tightly the min-max risk, and both the global and the local. So the local min-max risk is basically between these two quantities. Both of them behave like 1 over k. K is the number of bits, and there's some constant that depends on the correlation, which is almost tight. So this is there's some 1 over 2 ln 2, and there's some constant that is not exactly the same for the upper bound and lower bound. It's almost tight. And the interesting thing is, well, first of all, you can see that the worst case for the lower bound is attained at correlation 0, which makes it, this is the hardest correlation to separate from. And at that point, these two bounds coincide, so this gives you exactly the global min-max risk. Okay, so R star, the global min-max risk is 1 over k times 1 over 2 ln 2 plus some negligible things. Nicely, this behaves as 1 over k, which in a centralized case, if you will, the min-max risk would behave like 1 over n, which is the number of samples. Okay, we've seen that before. And here it's kind of like bits and samples. There's a constant exchange rate between them. Another interesting point is that this performance, the global min-max risk, can be actually obtained by a non-interactive protocol. So interaction doesn't help you. Okay, it might help you a little bit in the local risk, but not with the global risk. Okay, so just a quick tour of related work. This whole genre of works on parameter estimation under communication constraint probably arguably started with the work of Zhang and Berger in '88, and there's a bunch of other works after that by Sweated, Bornashev, and Han and Amari, and so on. These works are a little different than ours. Mostly they're considering one-way communication, and then they have a coupling between k and n, so they're working at some positive rate. And ours, you can think of it as 0 rate. And our bounds, our lower bounds specifically, cannot be recovered from these works. The most closely related work, surprisingly for me at least, was actually coming from computer science. And I have to thank Rotem Oshman for this, because I've never heard of that. So there is this problem called the gap Hamming problem. It's a very central primitive in communication complexity. And the problem is this is introduced by Indick and Woodruff in '03. So the problem is Alice and Bob observe two binary sequences, x and y, and there's no distribution. And there is a promise that the Hamming distance between x and y is either n half plus square root of n or n half minus square root of n. So they're very close to being unbiased. And the goal is to reliably distinguish between these two hypotheses with some really reasonable error probability with minimal communication. So they ask what is the communication complexity of trying to distinguish between these two things. And surprisingly, this was pretty hard to show. It took about 9 years until Chakrabarty and Regev in 2012 showed that the complexity, communication complexity, the number of bits you have to communicate interactively is omega of n. So essentially, you have to send everything. Right? Essentially, there is nothing short of Alice just describing to Bob what she has, and then this is trivial. And it turns out that our result implies this bound. It's a little stronger than this bound because it also gives you constants when you assume distributions, and also provides the first information theoretic proof of this result. So it was proven by different means. Other related problems is testing instant dependence with communication constraints, started by work of Valswed and Cesar, and with some follow-ups by Young-Han Kim and his student, and Tiagi and his student. And the reason it's related, you'll see in a minute, is because we are actually reducing the testing instant dependence. Another collection of problems which is less closely related is a set of problems of statistical estimation with high-dimensional distributions with a lot of players. You've heard talk by Ofer this morning about this. This is a little different than our setup because there's the same distribution given to multiple players, and the issue is the high dimensionality of the problem. Here we have two components of the same distribution, and we're trying to estimate correlation, so it's slightly different. And one thing that is actually central, and maybe not clearly why, is the problem of interactive common randomness extraction. And specifically this paper by one of our co-authors, Jingbo Liu, with Cuff and Verdu from 2017, which introduces something called the symmetric data processing inequality, which is central to what we do here, and we adapt it to our proof. All right, so today I'm just going to discuss the issue of global min-max risk to show you that it's 1 over k times 1 over 2 ln 2. This is actually the central thing, and I'm not even going to show you that. Okay, so I'm going to show you that. So I'm going to show you the 1 over k behavior, and I'm going to show you that 1 over 2 ln 2 is an upper bound. I'm not going to show you it's a lower bound. I'm just going to convince you that it works. All right, so for the upper bound, it's very trivial to get 1 over k behavior, right? Think about the binary model, for example. So Alice can just send her first k bits, right? And then Bob computes the correlation, which is empirical correlation, which is just the summation of average xk times yk. And if you look at the expectation of this quadratic risk, it is 1 minus rho squared over k. If you supermise over rho, you get 1 over k. So that's about it. In a Gaussian case, you can just take signs and get the binary set up. You change the correlation a little bit, but zero correlation doesn't matter. So it's the same. And the question is, how do we get the optimal constant, 1 over 2 ln 2? That's the only remaining question here. And it turns out that in order to do that, you have to use exponentially many local samples. Okay, so you have infinite number of local samples. You actually have to use the fact that you have so many. Okay. Here's a very simple way to see it in the Gaussian setup. So remember that in the Gaussian setup, we can think of y as being rho times x plus some noise that has a variance of 1 minus rho squared. Okay, this is a representation of the Gaussian setup with correlation rho. And what we can do is Alice can take 2 to the k samples, okay, and look for the maximal sample out of this, the largest sample she has, and send Bob the index of that sample, which you need to use k bits for that. Is that exactly what you have in store, right? And Bob just looks at the estimate, looks at the W, finds his own corresponding sample, YW, and he would have wanted to take the ratio of YW with XW, which obviously would be pretty good for you, right? But he doesn't know XW, so he just plugs in the expectation, which he can compute. And it turns out it doesn't matter. Even if he had known XW, you wouldn't have helped him, okay? And you can easily see that this is an unbiased estimator of rho, and using some standard results from extreme value theory, you could see that the expectation of this XW is square root of 2 lambda number of samples you're looking at, and the variance is 1 over log the number of samples you're looking at. And if you plug all those results in, you get that the variance is 1 over k, 1 minus rho squared over 2 ln 2. And the worst case of this is going to be 1 over k times this constant that we're looking at. And this 1 over minus rho squared can be improved with interaction to be 1 minus rho squared squared. Okay, so this is how you get the upper bound. For the binary case, there are 2 ways to do it. One is by reduction to Gaussian, by taking long blocks and using the central limit theorem. You have to be a little careful with that, but you can do it. And this is an asymptotic version. And you can also attain this directly in Hamming space. There's another way of attaining the exact same performance. I'm not going to describe this here. Okay, so lower bound, which is the more interesting part, I guess. So this is a high-level description. Let me write P rho of whatever there is as a substrate as the joint distribution under correlation rho. So I'm assuming correlation rho here. And what we do is we reduce the problem to testing against the independence. And we use this beast we call the symmetric SDPI, which I'll talk about in a minute. And what we're going to show is that the divergence between the distribution on Bob's side at the end of communication under correlation rho and under correlation 0 is upper bounded by rho squared times the number of bits that have been exchanged. And the same for x, of course. It's a symmetric thing. So, 5. Wow, all right. Okay, so let's see what happens. And you can see that from this, you can easily see that you get the 1 over k bound. Because if correlation is little o of 1 over square root of n, you cannot distinguish between 0 and this correlation. And so your mean square has to be of the order of 1 over k. And to get the sharp 1 over 2 ln 2 constant, you have to work a little harder. You have to relate the KL divergence to the Fisher information and then use the Bayesian Kerr-Rao lower bound, but I'm not going to do that here. Okay, and you can also get the local bound using a technique, a similar technique is being used by Rahman and Aaron Wagner by reducing to conditional dependence. But I'm not going to talk about that as well. Let me show you how you prove things in the one-way case. Okay, I don't know if I'm going to have time for the two-way case, but let's see the one-way case. Remember that the data processing inequality says that whenever you have a Markov chain UXY, then IUX is smaller than IUY, right? And the strong data processing inequality says, okay, let's try to plug in some constant there, okay? And S of PXY is the best constant you could put when, to make this inequality tighter when you have specific PXY. So this is well-known, and a well-known result dates back to Sweat and Gux, is a tensorization of this quantity. It means that if you have two independent samples from xy and x prime y prime, then their SDPI coefficient is the maximal SDPI coefficient from each one of them. Specifically, if you have a product of the same distribution, then the SDPI coefficient is just the SDPI coefficient of one component. And in the Gaussian and binary case, it's well known that this coefficient is exactly rho squared. So how do we use this? In the one-way case, the protocol is just the first message, right? There's just one message. And there is a Markov chain, pi, x, and y, by definition. And also the marginals do not depend on rho, right? Also note that pi and y are independent under zero correlation. Okay, so that's all we need to prove this. And if you look at the divergence between the distribution at Bob's side with rho and with correlation rho, correlation 0, then this is you could expand the right-hand side as a product because there's independence there. And then you could replace. It doesn't matter if you put zero correlation rho, because the marginals do not depend on rho, and that becomes mutual information between the protocol and yn, which is upper bounded by the strong data processing inequality coefficient times the mutual information between protocol and xn. This is bounded by rho squared, and the mutual information is bounded by the entropy, and then the entropy is bounded by k, and you're done. What is the problem with interaction? Well, in interaction, there is an ongoing process, and what happens is that the distribution of x and y, and given everything that has happened so far, is not a product distribution, right? So you can't apply the SDPI for the original setup. You need an SDPI that captures this. And what you can show, and what we show is basically this. We show that, first we show the divergence we're looking at. This is the divergence between correlation rho and correlation 0, is this difference between mutual information. This is a simple thing. Which you can think of as information exchange between Alice and Bob. This is the mutual information between x and y before the conversation, and this is given the conversation. And we show that this is upper bound by rho squared times the information injected by Alice and Bob into the protocol. So mutual information between x and y and the protocols, what somebody else learns from listening to the protocol. It is true for both the binary and Gaussian case. And y is, so we can call this en and exchange and injected, en and jn. And the proof is concluded because jn is obviously upper bounded by the entropy of the protocol, which is k. So you're done, and that's it. So if you prove this, then you're done. Okay. I'm not going to show you how to prove this. I'm just going to tell you that if you expand, oh, whoa, that was fast. If you expand these these two terms, the one that is exchanged and one is injected, according to coordinates, you get this kind of expansion. And then if you could prove an SDPI for each component, for every round, then you would be done. So you need an SDPI that is sort of the worst case over the round in some sense. You have to take care of how the distribution changes over time. That calls for an introduction of something called a symmetric SDPI, called S infinity of PXY, which is the smallest constant such that the exchange information is upper bounded by S times the injected information. And one way to do this when n equals 1 is by noting that the distribution of x and y, given everything that happened so far, is a tilted version of pxy. So what happens because of Bayes' rule is that the distribution is just the original distribution times some function of x times a function of y. It's not something more complicated than that. And you can define, so you can take the supremum over all such distributions. Define this S dagger constant, which is a supremum over all possible SDPIs for all possible tilted distributions that can happen throughout the protocol. This is a little more because some of these distributions cannot really happen from protocols. But nevertheless, you can do that. And then the S infinity that you're looking for is bounded between the regular SDPI and this new thing, S dagger. And we can prove that S dagger is equal to rho squared for both the boundary and the Gaussian case. Okay, and that completes everything for n equals 1. The problem is that S infinity dagger doesn't tensorize. Okay, so that's one issue. Actually goes to 1. But S infinity does tensorize, and this falls from some work by, again, by Jingbu, and also similar to what Kaspi has done in 85. Therefore, because we have that S infinity dagger was exactly equal to rho squared, and it's an upper bound on S infinity tensorizes, and then this upper bound needs to be tight, right? So we finally arrive at this inequality that we wanted that tells us the divergence between correlation 0 is upper bound by rho squared k, which we said is enough to conclude the proof. Probably out of time, right? So just a few more points. I hope that was not too fast. It probably was. There still remains some multiplicative gap between the upper bound and lower bound in the local min-mask risk. Okay, so that's one thing that somebody might want to look at. And I should say that our results hold verbatim, as is in the case of estimating correlations when pxy is completely unknown, subject to some minor moment conditions. If you think about it, the Gaussian is basically the worst case. So you can reduce everything to Gaussian, and then you're done. But there are some families, surprisingly maybe, there are some families of distributions with the correlation that cannot be learned from neither by Alice or Bob, regardless of how many samples they have. But R star, the min-max risk, is 2 to the minus some constant time k. Okay, so there are some families where the risk can decay exponentially with k. Okay, but in the worst case, the k is like 1 over k. And we might want to think about extensions to positive rate, the positive rate case, which hasn't been done. And there could be many other applications for symmetric SDPI and communication complexity, for instance, for estimating other functionals that are not separable like the correlation, okay, such as mutual information, various entropies, and so on. And that's all I have.